Okay, no problem. I was prepared for this. I have another desktop right here with the notes. So yeah, we can proceed. Okay. So yeah, thanks Gary for the nice introduction. The topic of my thesis was development of Josephson parametric amplifiers for quantum applications. And indeed, I mainly performed my thesis at TNO. So let me start by giving you guys a short introduction about quantum computing, because I think that might be nice.
Oh,
I think somebody has left their microphone on. Yeah, thank you very much, Hank. Yeah, so I thought this might be nice for my family and friends who are not familiar with any quantum applications. So quantum computing has become one of the leading applications of quantum physics, which is in theory that describes the world at the most fundamental level. So it describes how atoms interact with each other. Quantum computers have the potential to solve complex problems that are beyond the reach of even today's most powerful supercomputers. A common misconception is that they will replace normal computers. However, this is not true, as they are needed for the readout. So they always come in pairs. Here we see. Let me get my pointer. Yeah. Okay. So here we see a quantum computer, which is somehow coupled to the laptop we see here. So let's see how they differ. So classical computers encode information in bits. Each bit can represent a 0 or 1. These zeros or ones act as off-on switches that translate into a compute function to perform calculations. The more bits your computer has, the more complex problems it can solve. So just like a classical computer has bits, and a quantum computer has qubits. These qubits make use of two key principles of quantum physics. Superposition and quantum entanglement. So superposition means that each qubit can represent a 0, a 1, or both at the same time. And, quantum entanglement happens when two qubits are in a superposition, so they correlate with each other. This means that the state of one qubit, whatever it is, it's 0 or 1 or both, depends on the state of the other qubit. And so using these two principles, qubits can act like advanced on-off switches, helping quantum computers solve problems that are impossible to solve with normal computers. So we very briefly discussed how quantum computing works theoretically, but how are we going to do this in real life? So first of all, you need to have a superconducting quantum processor containing qubits. These qubits require cryogenic temperatures to work, which means that we need to cool this chip here down to 15 millikelvin, where 0 Kelvin is minus 273 Celsius. This is theoretically the lowest temperature you can have. So we do this with this is what it looks like from inside. So we place this quantum processor in the coldest stage of the delusional refrigerator, or also referred to as a cryostat, which is usually the lowest part. And we talk to the qubits with microwaves. So inside of the cryostat, we have all of these microwave cables that allow the user to actually go to the qubits and probe them with microwaves. And so this is what it looks like in the actual lab. So this white cylinder here is the delusional refrigerator. It cools the processor down to the required cryogenic temperatures, but it also protects it from the environment. So like from external radiation, like cosmic background radiation or even radiation coming from your phone. So before we dive into the content, I would like to acknowledge my supervisors who Gary already introduced. But yeah, without you guys, this project would not have been possible. So thank you. So moving on to the content. First I'll explain the role of amplifiers in quantum computers. So the amplification chain. Then I'll explain some theory about amplification, very basic amplification theory, but and I will also go in more depth into parametric amplification. After this, I will discuss an advanced parametric Joseon parametric amplifier known as the Joseon traveling wave parametric amplifier, or for short, TUPA. Then I will focus on the fabricated Joseon junctions needed for these amplifiers. After this, I'll focus on the cryogenic measurements we performed on the devices I fabricated. And lastly, I will discuss another type of Joseon parametric amplifier known as the GPA. And I will shortly point out some theoretical differences between the GPA and the TUPA. So we know we can probe our qubits with microwaves, but these qubits have quantum states that are very fragile. So they usually require a few photon energy to be probed. This is very little. Actually, the funny part is that you cannot buy any. So the typical single generator that you can buy has a minimum output power of milliwatts, which is still way too high. So we need to reduce the thermal radiation by thermalizing the signal in steps, decreasing its temperature. So here we see in the cryostat we used in the thesis. So this is the inside wiring of the cryostat. And I just want you to notice the decreasing steps next to the blue arrow here. So this goes from 15 millikelvin to 10 millikelvin, which is the coldest stage of the cryostat. So by sending a very weak signal through the qubits, one might understand that the readout needs not only to be amplified, but be amplified with high enough gain, but also with the lowest noises possible. So this is where amplifiers come into the picture. So amplifiers are actually very common in all electronics. An amplifier is anything that you put an input signal in and you get a larger version of that signal out. So let's say in this example, we see a boy with a triangle making a noise. The sound waves are absorbed by the microphone, and these go through the cable to the amplifier where they are amplified. And so the output signal is a larger sound wave. So we also need to take into account that everything is amplified equally. So also the background noise. So we need to watch out not to lose the signal in a noisy environment like here. So to get more technical about amplifiers, here we have an input signal. This can be anything we're interested in, but usually it's just a voltage or a current. We let this go through an amplifier, and the output of the amplifier gives us a larger version of the signal. So we see that the amplitude of the signal is increased, but the frequency remained the same. So the differences between the input and the output signal amplitude is called the gain. And this can also be seen as the ratio of the output-input power. And this is usually measured in decibels, which is a logarithmic scale of the power ratio. Lastly, also amplifiers also add some noise in the system. Noise is an unwanted but unavoidable effect that creates disturbance in the desired signal. So parametric amplification. This is another type of amplification which usually requires an external power source to modulate one parameter in the system. This power source is usually referred to as the pump. The added noise of this amplifier can be very minimal compared to other amplifiers, as the energy of the pump goes to an parameter inside of the system instead of being directly added to the signal. So here at the right figure, we see a schematic of parametric amplification. Here at the left, we see the two sources, so the pump source and the probe signal, which is the signal we want to amplify. We let these two propagate through a nonlinear medium where they interact. And so if the pump frequency is approximately twice the natural frequency of the signal, parametric amplification is reached. This interaction is according to, or is called four-wave mixing. And this is according to this formula. And since the nonlinear medium where the two signals interact is non-linear, the system will give rise to a third signal called an idler. This is due to energy conservation. And we see this same signal here in the formula as denoted as Fi. And so the nonlinearity in our devices is introduced by the Josephson junction. In the next slide, I will explain how parametric amplification is obtained by modulating one parameter. I remember during my first month at TNO, Dr. Nodar Samkarache explained parametric gain to me using an example with a person on a swing. I tried to recreate this using my little brother and his friends. So here at the left, we see the boys. And so the child in the middle pushes the swing. This is effectively the input signal. By standing and squatting, they're actually trying to change their center of mass, therefore also changing the length of the oscillator. This is the parameter they want to vary. And doing this at the right frequency, one can achieve parametric amplification. So we see here that their amplitude is way larger than when they started. So this was with an input signal. And we also tried to do the same experiment without an input signal, so with no starting push. And this example shows that you cannot have parametric amplification just by pumping by pumping nothing. You need to have like an input signal. Yeah, you can see that they tried their best, but they couldn't get the swing to oscillate. So parametric amplification for electrical signals works actually a bit differently, but this example just shows how you can get some amplification by modulating one parameter inside of the system. I don't have the time to compare this with the electrical case, but I would be happy to return on it in the Q&A. So moving on to the actual work done by me, I will discuss the fabrication of the Joseon traveling wave parametric amplifier, or the TUPA. So here we see an optical picture of the TUPA chip I developed. This chip contains 15 TUPA devices, and each TUPA device is basically an Joseon junction transmission line, Joseon junction based transmission line going from the left to right. And the fabrication was as follows. So here we see a small portion of this transmission line, which is here. We started off by sputtering and patterning a niobium titanium nitride layer on silicon. Then we deposited using an dielectric. This is used for the parallel plate capacitors. And the electric was deposited using PCVD, which is plasma enhanced chemical vapor deposition. And the electric we used is a low loss dielectric hydrogenated amorphous silicon. And lastly, we evaporated aluminum. So this was used for the top electrode of the capacitors here and here. And using, so with double angle evaporation, we also made the Joseon junctions. These are the cross-like features we see here. So the devices I fabricated consist out of a long chain of unit cells. And the TUPAs I managed to fabricate had 115 of these unit cells. So here's almost one unit cell shown. This is the corresponding electrical diagram of it. We have three Joseon junctions here with corresponding shunt capacitors to ground. These are the main transmission line elements. And lastly, we also have an RPM resonator. RPM stands for resonant phase matching unit, or just for resonant phase matching. And this element is used to manipulate the dispersion of the propagating wave. This is needed to optimize the gain of our devices. So this method is developed by UC Berkeley in America, and it's explained in the paper listed below. In the next couple of slides, I will discuss the fabrication of the Joseon junction, as the development of these junctions was a big part of my thesis. So the Joseon junction, or JJ for short, is the smallest structure in our devices. Therefore, it's also the most critical one. There are many types of Joseon junctions, but in general, they're just two superconductors being weakly linked with each other. And we used, for superconductor material, we used aluminum for both sides. And we used aluminum because it's easy to oxidize, which is needed for, which we used for the weak connection, or the aluminum oxide is also referred to as a tunnel barrier needed for these junctions. And there are actually several different ways to fabricate this type of Joseon junction. But the method I used is known as the bridgeless method. which is which creates the Manhattan-style junctions, or also known as cross junctions. So here we see a schematic of what's happening. We expose a cross-like pattern using an electron beam lithography on a B layer resist, and the lower resist layer is more sensitive than the top resist layer to the electrons, which creates an undercut needed for a liftoff, which I will explain later. So this method is actually very well described in the paper here. But the developed features are designed to be deeper than the width here, to allow the aluminum to reach the channel. So let's say to reach the blue line here, which is channel 1. If it's evaporated from this angle, but the features will block the aluminum in channel 2. So if it's the orthogonal channel to channel 1. To describe this in greater detail, I made some cross sections of the B layer resist stack I used, and so we see that during the first evaporation, the aluminum in channel 1 is evaporated, but for channel 2, the aluminum is evaporated on the sidewall of the resist stack, and after this, the sample is rotated for 90 degrees. And then, during this process, so during the rotation, we oxidize the aluminum needed for the junctions. So we make the tunnel barrier, and then we do the same evaporation again. But because we rotated the sample, the aluminum will reach channel 2, but for channel 1, the aluminum is evaporated on the sidewalls. And so the overlap area of the junction depends on the top opening of the developed resist, which is indicated with a double-sided orange arrow here in these pictures. So there were some fabrication issues I encountered during my thesis. One of these issues was crack formation next to the exposed areas. So the recipe we used for our junctions was used for smaller junctions needed for qubit devices, which have the typical widths of 100 to 200 nanometers. For our devices, we needed relatively larger junctions. Junctions above 1 micron, which is 10 times larger than the normal junctions. We did not have any experience fabricating these larger junctions, so we needed to explore a bit. And we did this by using a thicker B resist layer. However, using the standard recipe for the thicker resist layer caused some problems. So yeah, these crack formations here next to the exposed areas. This is actually very bad for the uniformity of the film, because we see here some whitish area which is not shown in other junctions. This can be very bad for the reproducibility of our devices. So we found that by using a cold developer instead of a room temperature developer, we can get rid of these cracks. So then we get something like this. And preventing the crack formation was actually just one of the fabrication improvements I developed. But anyway, moving on to the last process of the fabrication, we remove some of the aluminum. This process is known as liftoff. So here we see a SEM picture of a tilted top view of the junction, which is created here in the middle. A SEM picture is SEM stands for scanning electron microscope, and it uses electrons to make an image instead of optical light. And doing this will allow, because electrons have a smaller wavelength, we can create images with a greater detail, so with a better resolution. Liftoff process using a solvent that dissolves the beer layer resist under the aluminum here, causes the aluminum and the resist to lift off. So what's happening here? And so only the aluminum evaporated on the substrate will be left over. So here we see another SEM picture in which we see the Joseon junction after the liftoff process. After this process, you can clearly see the cross junction. And so the Joseon junction is actually formed in the middle where the two aluminum layers intersect. After the liftoff, the samples are diced into our final devices, into our final chip. So here we see our 2-pi chip again. Before we could proceed to the cryogenic measurements, we needed to contact one device to the cryostat. I will quickly go through some of the steps to connect the device. So first, we wire bonded one of the devices on a PCB. These wire bonds we see here connect the transmission line of the device to the transmission line of the PCB. And so the PCB is here, and the transmission line of the PCB goes to a coax cable here and here, which are the input and output. And then the PCB is mounted inside of a puck. The puck is then connected to a final shield we see here, and then it's mounted in a cryostat. And so after the mounting of the puck inside of the cryostat, we needed to cool the cryostat down to 15 millikelvin, which is the required temperature. And then we could proceed with the cryogenic measurements. So these measurements take a lot of time to do. So I only had time to do this in the final part of my thesis. And I did these measurements together with Dr. James Kroll. He helped me with this. And so one of the first measurements we did was a transmission measurement through the device. So this is the blue curve here, and in the y-axis we see the magnitude in dB, in decibel, and in the x-axis we see the frequency in gigahertz. And so we also so we compared this measurement with a cable through measurement, which is indicated with the yellow line here. For this measurement, we just discoupled the tupa from the puck, and we coupled a normal cable. So if we compare these two measurements, we found an almost 50 dB loss compared to the through measurement. which is actually a lot. This has a power ratio of 100,000. And so after unloading the TUPA device, we found a small niobium titanium defect connecting the transmission line to the ground. The defect is here, shown in the red circle. This could be a weak superconducting link, which can easily switch to a resistive state, causing a lot of reflection in the signal. And we also and so we used a scanning matrix, a scattering matrix simulation, and we found that this 50 dB transmission loss could correspond with a 20 milliohm resistor to ground. But before we unloaded the TUPA, we also did some measurements involving a pump. And so here we see the measurements. The blue curve is again the transmission without a pump, so the transmission of the TUPA, and the red curve is the transmission through the TUPA with a pump. And the green curve here is the difference between the two. This black line here indicates where our pump frequency is, what our pump frequency is. And so from this measurement, we saw that we can get two bands of 0.5 gigahertz in where we have 10 to 20 dB gain. So this is the band between 5 and 5.5 gigahertz and 7.5 and 8 gigahertz. With gain, I actually just mean increase in transmission. The transmission through the TUPA was always lower than the transmission through the cable measurement. So yeah, we expect that this great loss is due to the niobium titanium nitride shortage to ground. There are some ways to prevent or remove this kind of defects, but unfortunately, this didn't fit within the time planning of my thesis. And lastly, we did some spectrum analyzer measurements. So here we see a 2D plot where we swept the pump frequency while keeping the probe pump, we swept the probe frequency while we keep the pump frequency constant and 5.26 gigahertz, indicated with the orange line here. And so we swept the probe frequency from 5.075 gigahertz to 5.25 gigahertz, indicated with the green line here. And so we saw that this signal, so this sweeping the probe frequency, give rise to an idler frequency. And this was all according to the 4-wave mixing formula we see here. And so if we take a line cut, we can clearly see the three signals. So the pump frequency is in the middle, indicated with the orange dot. The probe frequency is the green dot, and the idler is the red dot. And the fact that we see this idler and that it moves symmetrically with a probe around the pump is a clear demonstration of 4-wave mixing, and is a clear indication that we have 4-wave mixing going on, which is an indication that we have parametric amplification. So we also invested some time in fabricating an other type of Josephson parametric amplifier known as the GPA, which is based on a resonant cavity instead of a transmission line. Instead of a transmission line with many unit cells. So GPA, the GPA I made is actually an LC resonator capacitively coupled to a feed line. or to a transmission line. However, there is a squid added here, which introduces the nonlinearity needed for parametric amplification. The squid stands for a superconducting quantum interference device, and it consists out of a superconducting loop with two Joseon junctions coupled to it, which are indicated with the X here. And so the fabrication of this device was actually quite similar to the TUPA device. So first we have, again, the niobium titanium nitride sputtered and patterned on top of silicon. Then we evaporated using PECVD, or we deposited using PECVD hydrogenated amorphous silicon. This was used for the dielectric. Here we see so here we see a large dielectric used for the capacitor in the resonator capacitor here, and a smaller dielectric used for the couple capacitor we see here. And lastly, we evaporated aluminum. This was used for the top electrodes of the capacitors. So a large one here for the resonator capacitor and here for the couple capacitor. And this aluminum evaporation was also used for the Joseon junctions, which created the squid here. So now we see two junctions. The design gives this type of amplifier in theory and higher fidelity, but unfortunately the cryogenic measurements proved that this device was not working as it should. So I'm not going to discuss these measurements with you now. However, I will explain some theoretical difference between the two type of amplifiers, and the reason why we were more interested in the TUPA results. So the fact that the GPA is based on a resonant cavity limits the amplifier with a gain bandwidth product. This means that there is a trade-off between the gain and the bandwidth. So here we see a gain curve of a typical GPA. And so the bandwidth, and so there is 14 dB of gain over a bandwidth of 35 megahertz. This amplifier can be used for single qubit readouts, but we really need a larger bandwidth if we want to. Okay, sorry for that. But yeah, we need a larger bandwidth if we want to read out multiple qubits. For this, and TUPA is a better fit. So like a GPA, it works with 4-wave mixing, but it's not limited with a gain bandwidth product. Here we see a curve of a TUPA and gain curve of a TUPA. It has 20 dB of gain over a bandwidth of 3 gigahertz. And so the fabricating TUPAs will benefit the community as a whole. The ability to amplify over a large bandwidth simultaneously makes the TUPA another key component of for the construction of a large-scale quantum computer. So to summarize, after my short introduction about quantum computing, I explained the amplification chain and the reason why we need to amplify weak signals. Then I explained a bit about amplification and more specific about parametric amplification and how we can get gain by modulating one parameter in the system. Then I focused on the fabrication of the Joseon junction and the fabricated parametric amplifiers, so the GPA and the TUPA. Both suffered from fabrication issues. However, we observed 4-wave mixing, which is a clear indication of parametric amplification. By doing more fabrication cycles and measurements, we can improve on the transmission loss by optimizing the design and fabrication recipe. So to conclude, by investigating more time in the lab, I believe great things can be achieved. It's just like the old saying, no pain, no gain. So thank you very much for your attention. And I would be more than happy to answer your questions if you have some.
Great, thanks.
Bravo.
Oh, okay. Thank you for this question. Pretty quick. Let me. Yeah. Which slide was this? Yeah. Merci. So I actually prepared the slide for this. We see here. Both examples are actually harmonic oscillators. And so for the swing case, we have a boy on the swing. And when he starts at the highest position, he has the most potential energy, but no velocity. And as he starts to go down, he converts potential energy into kinetic energy. And he also starts to gain velocity. And when he reaches the lowest point, he has the most kinetic energy and the lowest potential energy. And then when he starts to go up again, the velocity starts to decrease. So the energy starts to be converted from kinetic energy to potential energy. And this is in a way the same what's happening inside of an LC resonator. So if we connect an, so if we need to move a bit the screen. Okay, cool. If we connect an inductor with a capacitor together in the circuit, the current starts to oscillate as the GIF shows. And it will start to oscillate at a resonant frequency, which is determined by the inductance of the inductor and the capacitance of the capacitor. And so to keep it short, the inductor stores energy inside of a magnetic field, indicated with the green lines here, the B. And the capacitor stores the energy inside of an electric field. We indicated with just the black lines. And so the dance between the magnetic field and the electric field is actually quite similar to the dance between the potential energy and the kinetic energy shown in the swing example. So did I answer your question a bit clearly? No? Merci.
More questions? If you have a question, you can put it in the chat if you want, or you can also unmute yourself and just ask.
I cannot see the chat.
Let me check the chat for you. I don't see any questions in the chat yet.
Oh yeah, I see.
See lots of thank yous. You have a friendly crowd.
Yeah. I see. Very optimistic.
Can I ask a question then?
Sure,
yeah.
go ahead, Marius.
Hi. Thanks for the talk, Stephanus. It was very nice.
Yeah,
Very nice work.
thanks for joining.
Oh, let me open the. Yeah, so I had a question about these parallel plate capacitors
Mhm.
that you said you use for phase matching.
Oh, the LC resonator, you mean, inside of
So
the...
you had some capacitors, a
Yeah,
series of capacitors to, which I believe you said is for phase matching.
yeah, it wasn't just capacitors actually. It was this RPM unit here, so it is an LC resonator.
Yeah. Okay, so the resonator. So what does it do actually? Why do you need to phase match? Is it
So
is it does it have to do with high power driving or?
yeah, exactly. So if we use a pump, a strong pump next to a weak signal, the phase of the weak signal is altered and changed. And so we need a technique that kicks back the phase. I have a slide for this. Let me see. Here. And so what is actually happening is after a bit, the phase is kicked back together with the pump. So yeah, so to keep it short, it's just to optimize the gain, and so you won't get a lot of reflections. So if the first type of devices did not have this RPM unit, and they could not even transmit through the device because it was two-phase mismatched.
And is it power dependent thing or not?
Is it, sorry?
Is it power dependent, this phase matching? Like, do you have to design, because you designed it for where you, yeah, did you design, when designing it, did you have in mind the power of driving, or does it even matter?
No. I basically reversed engineered an already known tupa, which is the one, I think it's this one from the paper you see here.
Yeah. Okay, nice. And bonus question is, can you describe this phase matching in the swing example?
Yeah, sure. I can at least try. Oh, so wait, the phase matching of the parametric amplification?
No, the phase matching. Oh, it was more like a joke. I think
No, I don't think I can do that, sorry.
Yeah. Okay, thanks. Thanks a lot.
I see one question in the chat, and the question is, there are two questions actually. What could be the use of such an application that you researched? And then the second one is, what is a DUPA?
Okay, so I'll start with the second one first. And tupa is a Joseon traveling wave parametric amplifier, and it is basically the the device I made for my master thesis. And the first question was the application. So I think I can answer these two questions both at the same time. So this is what an actual tupa looks. This picture is taken from the paper here below, and it's just an amplifier used to amplify very weak signals, and it used more specific. It is used to amplify microwave signals. So this is typically inside of a frequency band, and here we see such a frequency band, and it's between 4 and 10 gigahertz. And this gain here is a measure of what the amplification is. So the input against the output power. And so we see that using this tupa, you can have microwave signals that are amplified with a 20 dB gain. So here is, I think, 20 dB over a large bandwidth, which you need for applications such as the quantum computer. I don't know who asked these questions, but I hope they are that my answer is satisfying.
Yeah, that's clear. I asked it, Stefanos. I was just
Actually, I have a
wondering.
follow-up question on that I would like you to answer since I'm not in the field so much.
Mm-hmm.
It's a TWPA, but people call it a tupa. Why do people pronounce the W like a U? Shouldn't it be a twipa?
So yeah, that's an that's a very good question. I don't know. To be honest, yeah, I don't know. I think it's just it's easier to pronounce like this, I guess.
It's a W, right?
Yeah.
That should be okay, maybe. Good. Okay, I think we're running